Hi everyone, so today I'm going to talk about SDN controllers in the context of the wide area network. What I'll do in the first few minutes is give an introduction into the concept, and then I will go on and talk about the enabling protocols needed to create a controller for the wide area network that operates in quasi-real-time. And so I'll talk about BGP-LS, which gives the controller visibility of the current topology of the network, and PSET, which allows the controller to create new LSPs completely from scratch and to modify existing ones. And then in the second half of the talk, I want to talk about some of the applications of this type of controller. A classic one is path diversity, but also I want to talk about ones which are driven by telemetry data received from the network, things like automated congestion avoidance, where you move LSPs away from congestion hotspots that you've detected using telemetry, or moving away low latency LSPs from paths where the latency's suddenly gone through a step change increase in latency. So here's the concept behind this type of controller. The key points that I want to make is that it's a live controller directly coupled to the production network, as opposed to being a sort of offline planning tool or a passive monitoring tool. And so it's taking part in some of the control plane protocols of the network to allow it to have this very strong coupling with the network itself. And it's receiving inputs from three main sources, as you can see by those blue arrows. So first of all, from the network itself, it's got visibility of the network topology through BGP-LS. It's got a lot of streaming telemetry coming in, giving it information about what's currently going on in the network, and also LSP status through the PSET protocol. And then also it's receiving inputs from a human operator via a UI, and also inputs from higher layer systems via a northbound REST API. And so on the basis of those inputs, it's making decisions about the paths that traffic engineered LSPs should take across the network. And it can be modifying the paths of existing LSPs or creating new ones completely from scratch. Now, this type of control has been shipping for 3 years now, and it's deployed in a variety of different types of networks, so ranging from telcos, ISPs, international transit providers, and high-end enterprises as well. Now, this slide really is the key one of the entire presentation, really, because what it's showing is a diagram of a closed-loop automation system. And these, of course, are very familiar in many parts of engineering. The same style of block diagram could apply to a cruise control on a car or the air conditioning system in a building. And so what you have, starting on the left-hand side, is the user requirements. What does the user want from this network? How does it want certain traffic to be handled? And so then the network controller is performing path computations and actually installing traffic engineered paths into the network itself or modifying existing ones. But then the network is a sort of living creature, and so you've got outside disturbances that are affecting it. You could have outages, fiber cut. You could have changing traffic patterns causing congestion. And so you need a way of measuring what the current state of the network is. And so that's where the telemetry plays a very important part. So by providing telemetry, such as what is the traffic on each physical link, what's the traffic traveling along each traffic engineered NSP, what's the latency currently of each link in the network, what are packet drop counts on each link, and that, coupled with certain protocol information, gives the controller a good visibility of what's going on in the network. And so that comprises the feedback part of this control loop. And so it takes that into account when doing its computations. So this is a classical control system applied to networking. And as you heard on Monday from the Google talk, streaming telemetry is far superior to SNMP to acquire this type of data in quasi-real-time. You can send it at much higher frequencies, and also it's much more accurate because you're not suffering from those averaging artifacts that we saw discussed on Monday. Now let's have a look at a couple of the enabling protocols that I've alluded to. So first of all, BGP-LS. So BGP-LS is the means by which the controller has visibility of the topology of the network, so the layout of the links and nodes and attributes of the links that the controller needs to know. Now, this diagram, by way of example, is showing a multi-area network. So it could be multiple ISIS areas, as denoted by those dashed lines, or it could even be a multi-AS network. Now, the scope of traffic engineering IGP extensions is per area, intra-area. And so, for example, router E in this diagram would know about the link between B and D and its attributes, or the link between D and F, but would know nothing about the existence of router H's link to K and the attributes there. And so the controller needs visibility into each of these areas. One way it can achieve that, you could just have an IGP peering between the controller and each of those areas, but the controller is probably not directly physically connected into those areas. And so you'd end up having to do an IGP adjacency over GRE tunnels or something like that, which gets a bit messy. Instead, you can use BGPLS. So a BGPLS speaker takes the contents of the traffic engineering database, other IGP information, packages it up into TLVs and communicates those over BGP. And so then by having BGPLS speaker in each of these regions, perhaps pairing with a couple of route reflectors and those pairing with the controller, in that way the controller can ingest all of the topology information network-wide. It can actually combine it into a unified end-to-end view in its own mind, and so can successfully create end-to-end LSPs across this multi-domain topology, which is notoriously difficult, as you know, in the distributed traffic engineering case. Now, a couple more words about the nuts and bolts behind BGPLS. So what it's doing is it's using TLVs to describe nodes, things like IP4, IPv6, loopback addresses, ISO address if it's an ISIS speaker. And then for link attributes, things like what's the bandwidth of this link, any admin groups that have been configured, IGP metric, and also things like adjacency SIDs if segment routing is being used, because those are covered by traffic engineering extensions to BGPLS. So that's BGPLS in a nutshell. Now, the other protocol which I want to talk about is Path Computation Element Protocol, or PSET for short. Now, what this has, on the one hand, is the path computation elements, which is the central controller, and then you have PCCs, path computation clients, which are the ingress routers of the LSPs that we're going to set up. And then between the PCE and each PCC, you have a PSEP session. And over that PSEP session, the controller can create new LSPs completely from scratch, or could modify existing LSPs. And very importantly, PSEP is a bidirectional protocol, and so the reporting in the opposite direction from the PCC to the controller is very useful, because that's how the controller knows that an LSP that's just been requested to be set up indeed has been set up according to its requirements. And during the lifetime of the LSP, it allows the controller to know that the LSP is still intact and up and running. Now, in a network, in principle, you could have 3 different types of LSP from the PSET point of view. And so what I'll do is talk about each of those in turn. So this is what I call a vanilla LSP. So this LSP could have been configured on the ingress router, months or years ago in the traditional way using CLI config. And if you turn on PSEP on this network and attach a controller, what will happen is that all of these LSPs will be automatically reported to the controller via PSEP. And so the controller will be aware of the existence of all of these LSPs and all of their attributes, the precise path that the LSP is following across the network, a bandwidth reservation if it's an RSVP LSP, and so on. And so from the visualization point of view, this is very useful, because you can see the path of the LSP in the UI of the controller, which is much easier than poking around in the CLI of the respective ingress routers around the network. Now, the PCE is not authorized to modify this type of LSP. It's not been granted permission. On the other hand, there's another type of LSP which is delegated one, and in fact, the LSP that we saw in the previous example, you could convert into a delegated LSP. So typically, it's just a couple of lines of extra CLI config on the ingress router, which is giving delegation to the controller. And so what will happen is a PSEP message is sent from the ingress router to the controller saying, this LSPY, I'm delegating it to you. You've got permission to make modifications. And then over the lifetime of the LSP, the controller can modify the path of the LSP as needed, for example, to avoid congestion or to allow maintenance on a node that the LSP passes through. And so to do that, it would send a PSEP message to the ingress router, PSEP update message saying, this LSP, I want to change its path from ABC to XYZ. And so the ingress router responds by modifying the path accordingly. And then the final type of LSP is PC initiated. So that's one that's actually created by the controller from scratch. So the first thing that the ingress router knows is that it suddenly receives a PSEP message, a PC initiate message from the controller saying, hey, I want you to set up this new LSP. This is the name of the LSP. This is the precise ERO that I want the LSP to follow. Other attributes, bandwidth reservation if it's an RSVP, LSP. It will have a flag saying whether it's to be instantiated using segment routing or RSVP. And so then the ingress router actually instantiates it and very importantly sends a PSEP report message back to the controller saying, yes, this LSP is up and running in accordance with the requirements that you stipulated. And so in that way, the controller knows that what it's asked for is what actually exists in the network. So that's PSEP in a nutshell. Let's now have a look in particular at PSEP for segment routing. So with that, one way of creating a traffic engineered SR LSP is by encoding it as a stack of adjacency labels. So if you've got n hops in the end-to-end path, then you'll have n-1 adjacency labels, because you don't need a label for the first hop, because the ingress router just pushes it in the required direction onto the required link. And so the controller's been asked to compute this LSP, shown in green. Perhaps it's the lowest latency path between A and Y. It's computed the path as ALMNY. It's looking at what the adjacency labels are on each link, which it knows through BGPLS. And so to make the traffic follow that path, you need a label stack 406, 607, 708. And so the PSEP message sent by the controller will have that label stack, the associated IP addresses, and so router A receiving that will actually instantiate that in its ribbon fib. And so it will put in an entry typically pointing to router Y's loopback address. And so traffic going to destination Y would resolve over that. So that's how you deal with the segment routing using PSEP and controllers. So I've talked about the enabling protocols and other ingredients such as telemetry. Let's have a look at some applications. One very popular application is for path diversity. So you have end customers migrating away from SONET SDH private circuits. They want something of a similar, sort of look and feel. And often when they buy a private circuit between two different cities, rather than just buying one single circuit, they'll buy a pair for resilience. And they want those two pairs to be diversely routed. They mustn't share any links or nodes in common, so that if something breaks in the network, at most only one of those will be affected. So you need a pair of LSPs to underpin, that diverse pseudowire service, let's say. And those two LSPs are of equal status. It's not really primary, secondary. Both are up and running and active at the same time, and the customer can use them as they want. They could ECMP traffic. Some customers actually deliberately send duplicate traffic down both LSPs simultaneously for things like broadcast TV contribution feeds or financial market data feeds. It could be point-to-point LSPs or equally point-to-multipoint LSPs, and so then you need to do a diverse path computation for the point-to-multipoint LSP pair. Now the thing is, if you ask the two ingress routers, PE1 and PE2, to do the path computation, then there's no mechanism for them to collaborate as to making them diverse. There's no protocol mechanism for that. And so they would each do their path computation independently. And in this diagram, where you've got lots of ECMP paths in the network, there's only one chance in 16 that they're actually going to be diverse. So 15 times out of 16, they're going to share fate, as shown in this example, where actually they've got a node in common somewhere in the middle of the network, which means we're violating the path diversity service requirements. In contrast, if you tell the controller, look, I want a pair of LSPs, I want them to be diverse, these are the ingress routers, these are the egress routers, it will do the path computation as a simultaneous path computation, bearing the diversity requirements into account, and it will do it properly, and you end up with something like this, which is what you want from your service point of view. Another class of use case which I think is extremely interesting, this is my favourite one, is, it's going back to this closed loop automation which I talked about near the beginning of the talk. So the controller knows through streaming telemetry how much traffic is travelling along each physical link. It knows through streaming telemetry how much traffic is being launched into each individual traffic engineered LSP. And so you could set a threshold. You could say, okay, if the traffic on any physical link exceeds 90%, then move away some LSPs automatically to mitigate the congestion. And so in this example, in fact, the link which is coloured red has exceeded that threshold. And so the controller looks at what LSPs are passing through that link, and it decides which LSP or which LSPs are best to move away to ease the congestion. And of course, in so doing, it needs to redo the path computation such that it's not causing congestion elsewhere. And so having recomputed the paths of some of those LSPs, it sends PSET messages to the ingress routers with the details of the new paths, and the ingress routers move the LSPs in a make before break manner, so you're not actually interrupting the traffic. And so in this example, the blue LSP has been chosen to be moved and gets moved away, and so eases the congestion on that link that had been congested. And so this is a fully automated closed loop automation. So traditionally, this type of so-called traffic engineering people have done manually. It's quite labour intensive. Somebody's got to realise that a link's got towards a congestion point. They need to recompute the paths of some LSPs. It's quite tricky to do that manually. Then they need to log on to the ingress routers and put in some loose hops to pin the LSP away from the congested area. After a few months of doing this, you end up with a rat's nest of LSPs which have been pinned around the network in all sorts of different ways, and unravelling it can be quite messy because the reason why some of those LSPs have been pinned in a certain way may have gone away. So having a controller do all of this entirely automatically makes a lot of sense, as you can imagine. There's other triggers for moving LSPs. I mean, this congestion was one example, but another trigger could be interface error counts. And so a sort of really insidious type of fault is the so-called grey fault, where an interface is still up and running from the protocol's point of view. BFD packets are still getting through, but perhaps you're losing 1 in 1,000 packets or so, which could be enough to disrupt some end-user applications. And so the controller, seeing these interface error counts, can decide to move away LSPs from the affected links so that somebody can troubleshoot, perhaps clean the fibers and things like that. Another trigger can be queue high watermarks. So if you've got telemetry that is actually reporting what's the highest fill level of each queue on the link, has a queue got towards, in danger of overspilling, and so proactively you can move traffic away onto other links to prevent, microbursts actually overspilling that link. And planned maintenance as well. It doesn't have to be telemetry-driven motivation for moving the LSP. It could be you saying, at 2 a.m. I want this node to be put into maintenance, and so automatically the controller moves away all the LSPs just before that 2 a.m. Start time. Another angle is programmable cost functions. So typically these controllers by default are going to compute the shortest IGP metric path that meets the other requirements of the LSP, such as path diversity or bandwidth requirements. And so in this example, given these IGP metrics, the lowest metric path between X and Y is as shown by that blue arrow. On the other hand, people might have low latency traffic, and that low latency path could be different from the lowest IGP metric path, especially if the lowest IGP metric path denotes monetary cost. Classic example is if you're sending traffic from London to Singapore, the lowest latency way of doing it is directly eastwards around the globe, but the lowest monetary cost is send it the long way around the globe, sort of westwards, which is more than twice the latency. And so you only want to put the latency sensitive traffic onto the low latency LSP. And so what you need is a means to, first of all, know what the latency is. And so what would happen is the routers are measuring the latencies to their nearest neighbors using timestamp packets, something like TWAMP, reporting that with streaming telemetry to the controller. And so the controller can see what the latency is on each physical link at this moment in time. And so in fact, at the moment, the lowest latency path between X and Y is on the north side of the network, in contrast to the lowest IGP metric path, which, as you'll remember, was on the south side of the network. Looking at this latency type of use case in a bit more detail, often you get network operators renting capacity from WAN providers. So this might be a global network. You've got this operator renting capacity on transoceanic cables from WAN provider X and WAN provider Y to give some degree of resilience. What can sometimes happen is that you get a step change in latency, which you don't know exactly why it happened. It might be a fiber cut within one of these WAN providers, but you need to mitigate against it. And so in this example, at the moment, the latencies are shown by those numbers on each link. The dominant latency is across these transoceanic cables. And at the moment, the lowest latency between PE1 and PE2 is, as shown by that red LSP, and the controller's computed that path as being indeed the lowest latency path. Now what happens, there's a fiber cut in WAN provider Y, step change in latency on that link from 11 to 23. The controller sees that through the telemetry reports, and so it automatically reassesses the paths of all the low latency LSP that pass through that link. It redoes the path computation, and now the best path for this red LSP is along the north side of the network through WAN provider X. And so the controller sends a PSET message to the ingress router via PSET saying this is the new path for this LSP, and PE1 being the ingress router changes the path in a make before break manner, so you're not affecting any of the traffic. Again, you know, if you're doing this manually, somebody's got to notice, first of all, that the latency's gone up. It might be the end customers who start complaining because their applications are misbehaving. Then you've got to, you know, work out what the latency now is on each link, redo the path computation, you know, configure a new ERO on the ingress router. You know, quite labor-intensive and cumbersome. So doing it, you know, completely automatically in this closed-loop manner, you know, is obviously a lot more efficient. So that brings me more or less to the end. A few references if you're interested in learning more about this whole topic area. First of all, a webinar, the first URL, which is a deep dive into PSEP and BGPLS. So this really goes into the nuts and bolts. It shows packet dumps, for example, PSEP packet dumps when you have a PCE-initiated LSP. What does that PC initiate message look like? What's the message that goes back to the controller from the ingress router? Things like that. Then a reference linked to the PSEP working groups. There's 10 years worth of drafts and RFCs stretching back over time. You know, you'll see recent ones like PSEP extensions for point-to-multipoint LSPs, PSEP extensions for segment routing. Then the BGPLS RFC. If you're interested in particular implementations, you can read about ours, which is called North Star. And then finally, a few blogs which I've written on related topics. So that's it. Thanks a lot for your attention. I don't know if anyone wants to ask any questions, or if not, I'll be around you know, in the hallways afterwards. So thanks a lot for your attention. Okay, no questions. Thanks a lot.